Now, the objective of these next lectures is to reach the Riemannian curvature, you see, embedded in R3. Now, let's say lecture 25, parallel transport from A to B. It's just a review, you see. Now, consider a smooth manifold M with a connection defined by the Christoffel symbols. You see, this is capital gamma ijk. This is a connection. Okay, so the curve gamma from lambda A to lambda B. Attention, lambda A and lambda B belongs to the real. You see, as we pointed out, emphasized previously, this lambda A, that's a map, okay, from lambda A to a point. A is a point in the manifold. B is the point of the manifold. We call these points as a label, okay? Now, this A and B over here defined by this way. Now, covariant derivative. This is a covariant derivative of a vector VA. This is a component, vector VA, along the curve AB. Curve AB belongs to the manifold, okay? All the points are labeled. You see, that's a very important consideration. Now, let the coordinates of the curve xi of lambda, again, I insist, xi are labeled, okay, where lambda is the parameter. The tangent vector to the curve is ti, attention, ti is the derivative of dxi with respect to the lambda, okay, and this derivative here is obtained, okay, not on the manifold, okay. That's as we also we pointed out before. So these points belong to the manifold, but the derivative are calculated, are obtained outside the manifold. By definition, the covariant derivative, okay, of a vector, this is VI, this component, okay? Attention, this is a contravariant component which belongs to the vector space. Now, along the curve is, okay, this is capital D. Sometimes you see in the literature, you substitute this capital D by the operator, okay, capital delta, like this, you see? You just substitute, okay? This is the same, okay? This is other notation. So this is dvi, d lambda, plus, this is a Christoffel symbols, okay? dxj, dx lambda, vk, you see? Now, in the next video, I will derive, okay, all this relation over here, you see? That's step by step, as you see on lecture 26, 27, and so on. Again, the objective is to derive the Riemann curvature, okay? Now, this is one, okay? Now two, parallel transport, okay, from A to B. Parallel transport, VI, is moved along the curve gamma of lambda without twisting or rotating, okay? That's what we call a parallel transport. Now, this movement, I will move this relative to the manifold connection. So I will impose, okay, the covariant derivative with respect to lambda will be 0. So this I set here 0, and then in this I represent the VI of the lambda is minus VK, this is Christoffel symbols, and Tj, okay, there's a tangent vector, okay? So again, I is free index, okay? that's important here. This is the first order system, okay, of linear ordinary differential equations for VI of lambda. Again, I, okay, is a free. Okay, that's why you have a system of ordinary, this case, ordinary differential equation. So this given the initial condition, you see, this here, okay, I have to give the initial condition of A to obtain this point B, okay? That's, so VI lambda A, VIA, okay? This is known, okay? That's the initial condition. So the solution gives VI of lambda B, okay? VI of B, you see? Which is the parallel transport vector at point B. That's important. Just for you to see that to obtain, okay, the parallel transport, I have to solve, okay, this ordinary differential equation. That's it. Again, I would like to emphasize that we are preparing just to obtain the Riemann curvature, which use, okay, parallel transport, okay, in a closed loop, as you see the next videos, next lectures. See, that's it.